Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today we are continuing with our series on writing a ray tracer in C++ using, as far as possible, only the standard libraries and the SDL2 library so that we can display results in a window. Using SDL2 to do this, of course, means that all of the code we write should be pretty much as multi-platform or cross-platform compatible as possible. So although I'm using Linux, you should be able to follow along these tutorials just as easily in Windows. So today we are going to talk about ray tracing versus ray marching. And I thought that, although this is a series on writing a ray tracer, and I'm not going to deviate from that, we are going to continue with ray tracing. I thought since ray marching is such a popular and versatile technique, it would be worth spending a little bit of time just to talk about ray marching, and in particular how ray marching compares to ray tracing. So in this video today, what we're going to do is look at the basics of ray marching and how it works. I'll show some quick examples. I'm not going to go into too much detail. And then I'm going to go on to look at the code and show the code in C++, and how we can implement ray marching into the ray tracer that we have been creating so far over the previous 12 episodes. So this will then be, the idea is that we can then fuse conventional ray tracing and ray marching together within the one system, which I think is pretty powerful. So that's what we're going to talk about today, and I really hope that will be of interest. If you like this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. Thank you very much. Right, well, without much further ado, let's jump into it and let's have a look at what ray marching is all about. Okay, so here we go. This is episode 13 now, and as I just said, we're going to talk about ray tracing versus ray marching. So just quickly before we get into that, I want to recap a little bit about how shapes are defined in traditional ray tracing. We've covered this before, so this is really just a bit of a recap. And we can recall how we originally defined a sphere using the implicit form, which is given by x squared plus y squared plus z squared minus r squared is equal to 0. And we can define that as a function of x, y, and z. Fx, y, z is simply equal to x squared plus y squared plus z squared. This then tells us that for any point, x, y, z, on the surface of the sphere, the value of fx, y, z is going to be 0. And for ray tracing, we simply combine the above with the equation for a line, which could be given in this form that you see here. X, y, z is equal to px, py, pz plus t, vx, vy, vz. Or in vector form, this would be some vector, say x is equal to p plus tv. And we can combine those two to give this equation that you see here, px plus tvx all squared plus py plus tvy all squared plus pz plus tvz all squared minus r squared is equal to 0. And then we can solve that for t. And that is basically how we do traditional ray tracing. We simply replace our implicit form equation with the implicit equation for whatever shape we want, and then we do these necessary calculations to solve for t, and then we can use the value of t. We can back substitute the value of t back into the equation for the line, which is in this case the ray, and then we can calculate the location of the point of intersection very straightforwardly. But one thing that we've never looked at in this series so far anyway is what happens to the value of fx, y, z for points that are not on the surface of the sphere. We know that on the surface of the sphere, fx, y, z is always going to be 0. But what happens to x, y, z, to fx, y, z when we're not on the sphere? Okay, so in this animation, we're going to have a look at exactly what happens to those values. So we have our function fx, y, z defined as x squared plus y squared plus z squared minus r squared. We have our equation for the line, and then we can actually then define our implicit equation as a function of t. So all I've done is simply replace x, y, and z here with px plus tvx, py plus tvy, and pz plus tvz. And so then we have a function f of t, and we can plot that for the various values of t, starting with f of t, starting with t equals 0, which gives an initial value of f of t is equal to 9. And you can see that as we move through the animation, as you can see, the red marker here indicates our current point along our ray, and we see in the plot on the background we have the quadratic equation, which we would expect because the implicit equation for a sphere is a quadratic. And most importantly, we see that at the points of intersection where the ray intersects with the sphere, the value of f of t is 0. I mean, in the case of a sphere, after some rearranging, we can get this equation here, which is a quadratic in the form of at squared plus bt plus c is equal to 0, where a is the dot product of v with itself, b is equal to 2 times the dot product of p and v, and c is the dot product of p with itself minus r squared. And we can then simply use the standard quadratic equation of t is equal to minus b plus or minus the square root of b squared minus 4ac over 2a in order to solve that for the values of t. And that's really very straightforward. That will give us the values of t where the function f of t crosses the 0 line, or on the plot that we just saw, which we see corresponds to the points of intersection between the ray and the sphere. Okay, so when we can find an analytical solution, then it is easy to solve for t and determine the location of the point of intersection, if indeed there was one. But let's think for a moment, does that actually work in every case? And let's consider the slightly more interesting shape, the torus. Everyone likes a shiny donut shape, I think, or a torus shape, so here we go. I think it makes a good example to consider. Now, the implicit equation for a torus can be expressed in this form here, where we have the square root of x squared plus y squared minus r major, and you can see r major and r minor illustrated on the picture here, all squared plus z squared is equal to r squared minor. I'm not going to go over the derivation of that in any way. Let's just for now take that as a given. There are plenty of resources on the web that talk about that if you want to know more. So the thing is, now we can rearrange that equation. If we let a equal the square root of x squared plus y squared, okay, then in which case we get that a minus r major all squared plus z squared is equal to r squared minor. And we can rearrange that, and eventually, I won't read through all of those steps, eventually we get to a form here where we have x squared plus y squared plus z squared plus r major squared, minus r minor squared, all squared is equal to 4r major squared times x squared plus y squared. Okay, and that is actually a quartic. If you were to expand this term in the brackets here that's all squared out, you would eventually get a quartic, and then you could rearrange it into the form of ax to the 4 plus bx cubed plus cx squared plus dx plus e equals 0. So, to find the points of intersection between a ray and our torus shape, all we have to do is find the roots of that equation, right? That should be straightforward. Oh yes, but unlike with quadratic equations, such as the sphere, there is no general analytical solution for the roots of a quartic equation. So, we cannot simply derive an equation for the possible values of t based on the parameters of the torus and the cast ray. Instead, we have to rely on numerical methods to find the root of the equation. Okay, now we should note here that I'm interested in the general case of finding the roots of any order of equation, not just quartics and not just for the torus shape. And because of this, I've taken a very general approach to creating a solution to this problem. Now, before we jump in and consider how to find the roots of this equation, let's have a look at what the values of fx, y, z look like, just as we did for the sphere. Okay, so exactly as we had before, we have the implicit form of the equation here on the left, and the explanations of how we can express that as a function of t for the particular ray that we are considering, which of course is shown here in yellow with the red marker as we saw before. And what we're going to do is look at what happens as we move our marker along our ray, the yellow ray, and we can see what happens to the value of the function of f of t in this plot here in the back. As before, we see that at the points of intersection, where the ray intersects with the torus shape or the donut shape, we see that the value of f of t is 0, and we see that we have 4 points of intersection. So there are 4 zero crossings, okay, 4 roots to the equation, which is what we would expect for a quartic. Okay, now it's interesting to consider what would happen if we were to move our ray. So clearly here the ray is passing through the center of the torus, so it's definitely intersecting with the torus 4 times. Let's just have a look at what happens if we were to move our ray. Now this is quite interesting. We see as we move the ray away from the center of the torus, the number of intersections changes. So at this point here, we see that there are indeed only 2 intersections because we're passing through the body of the torus itself, and we see that reflected in the plot of f of t here in the background as well. And obviously, once we're outside of the torus completely, then we no longer get any intersections at all. Okay, so there we go. But how do we actually go about finding the roots of that equation? Well, we're going to use something called Newton's method. This is perhaps the very simplest way of doing things. And if you're starting to wonder when I'm going to get onto ray marching, do not worry, very soon. But I wanted to cover this first because it provides a good deal of context about why ray marching is as good as it is. So let's go back to the equation for a sphere to start with, because the torus is quite complicated. So we'll start with the sphere. Okay, we have the equation for the sphere here, and we can express that as a function of t, since we know p, v, and r, and then we simply need to solve f of t equals 0. Now, Newton's method, I'm not going to go over the derivation. I might make another video in the future looking at how Newton's method works and everything else, but for now we're just going to take it as a given. And it's given by this iterative equation that t of n plus 1 is equal to t of n minus f at t of n divided by f prime of t of n, okay, where f prime t of n is the derivative of f of t at t of n, okay? So we simply have the ratio of the value of our function at a given point to the gradient of that function at that point, and we subtract that ratio from the value of t, and that gives us our next value of t, and then we simply iterate through that process to our successive values of t until we reach some kind of convergence. Okay, and as I said, this will give us successive approximations to the value of t that corresponds to the root. Now, to make this work, we need to choose a starting point, t0, and ideally this should be as close to the root as possible. And this is our initial guess for the location of the root. We then iterate through t1, t2 up to tn until either we achieve convergence or we exceed a certain number of iterations. We have to have the second criteria in the case where perhaps there isn't an intersection, so we don't let it just run forever. So let's have a look at how this works. Okay, so I've gone back to the example of the torus because it's really much more interesting than dealing with a sphere. And as before, we have our implicit equation here as a function of x, y, z, and we then express that as a function of t by getting the values of x, y, and z from the equation for the line. And then we have the Newton's method equation here, tn plus 1 is equal to t of n minus f of t of n over f prime t of n. And below here we have the value. So t1 is equal to t0 minus, and for t0 is equal to 0, because we're starting at 0, which is the initial point of our ray, and usually that would be the location of the camera. We have values of f of t of 79 and a value of the gradient of minus 113. Okay, now let's have a look at what happens as we iterate through this process. So the first iteration, we see t1 now jumps to 0.701, and we can see that it's now got a lot closer to the point of intersection. F of t has now become 24.3 and f prime of t is minus 49. Okay, so we could then pump or simply drop the value of t1 into this equation here, and we get the value of t2, which would give us this. So t2 comes out at 1.198, and then t3 is 1.534, and you can see as we go through this, the extent to which the value of t is changing is getting smaller because we're converging to our solution. And also notice the values of the gradient are getting smaller as well. Okay, so t4 becomes 1.738, t5 1.836, t6 1.861, t7 1.862. So you see we're really starting to converge now, and the value here of f of t has become very, very close to 0. 2.17 times 10 to the minus 5, that is extremely close to 0. So we could in principle stop here and say that the value of t, but we continue through, there we go, to 10 iterations, which then gives a value of the value of f of t at that point is 8.9 times 10 to the minus 16, which is incredibly close to 0. So we can say that the value there, t10, that we would work out from that equation, which would be, yeah, there we go, 1.862, that is the location of our root. Okay, so, I mean, that's pretty straightforward. So surely that just means that we can solve whatever we want. Well, unfortunately, no, not quite. Let's consider a slightly different example. Let's just move our ray over here like this, so that now the ray no longer passes through the center of the torus, and in fact it now passes through a point at what would be the back face, the back side of the torus, of the body of the torus, with respect to our starting point. And let's have a look now what happens if we iterate through that process as before. So as before, we start with t0 is equal to 0, and we get f of t then in that case is 112, and f prime of t is minus 140 or so. Now let's iterate through. So okay, t1 becomes 0.799, that makes sense, we're moving in the right direction. t2 becomes 1.396. T3 is 1.85, so we're definitely getting closer. T4, 2.223, T5, 2.67, now T6, 5.9 or 6. Okay, so clearly something has happened, and this is a real limitation of the Newton's method in this context. So if we were to continue, we see now what happens is our point of intersection, our marker, is now coming back towards the what would be actually the back face of the torus, and if we keep stepping through, we end up with a value of t of 4.5. Now that is a point of intersection, okay? That is a real root of the equation, as you can see on the plot at the back. So it's not wrong, but it isn't the root that we wanted. It is the back face of the donut, not the front face with respect to where we started with our ray. So this is a problem. So clearly we can't just simply use Newton's method in this basic way in order to solve this problem. And actually that quite neatly leads us on to the question of ray marching and why we might want to consider using ray marching instead. Okay, so let's talk about ray marching and signed distance functions. Okay, so there are ways that we can expand on the basic Newton method that would help to solve this problem, and I'm thinking that I will probably cover that in a future video. But it turns out that there is another approach that can help, which is ray marching. Okay, so rather than attempting to solve the implicit equation for the surface, ray marching works with the signed distance function, or SDF, of the surface. The SDF is basically a map of the distance from every point in space to the closest point on the surface of the object. It's called a signed distance function because the distance values are positive outside the shape and negative inside the shape. Let's look at the SDF for a simple sphere. Okay, so for a simple sphere, we have our signed distance function is given by the square root of x squared plus y squared plus z squared minus r squared. Note that that is subtly different to the implicit equation because we now have the square root. Okay, and actually that is a typo. That should be r, not r squared. Apologies for that. Anyway, so if we evaluate that for values of x between -3 and 3, values of y between -3 and 3, and a particular value of z, we're going to start at -2, then we see that we get something like this. Now, if we run through the different values of z, what we see is that at z equals 0, we very clearly have a circle defined in this plot in the center. So black gives a value of 0, blue is negative values, red is positive values in this plot here. And so clearly we have values of 0 that correspond to the boundary of a circle, or actually in 3D it would be a sphere. If we continue with that, we can see that as this plot moves back down, we see that we do indeed get a sphere that corresponds to that. Okay, so that is the basic signed distance function for a sphere. Okay, so notice how the signed distance function for the sphere is not quite the same as the implicit equation. So the implicit equation was given by fxyz is equal to x squared plus y squared plus z squared minus r squared. Okay, the signed distance function is given by fxyz is equal to x squared plus y squared plus z squared minus r. I do apologize, that should be minus r, not minus r squared. Okay, and this is because the SDF gives the distance at each point fxyz rather than the value of the implicit equation. Okay, so let's look at a different example. Let's go back to our torus shape. Now in this case, the signed distance function is given by an expression like this. And again, I'm not going to go over the derivation. There are plenty of resources online, other resources online if you want to look those up. So if we define a variable p is equal to the square root of x squared plus y squared minus r major, the major radius, then we can define fxyz, our signed distance function, as simply being the square root of p squared plus z squared minus the minor radius. Okay? And it's actually very interesting to look at that and think about it geometrically, because this equation for p is simply describing a circle of radius r major, right, in the xy plane. And then this equation, the final equation for xyz, actually defines a circle again, but in this time it is in the pz plane of radius r minor, which really makes sense if you think about the shape of a torus. Anyway, so notice how that is quite different to the implicit equation expressed here in its expanded form. Okay. So it turns out that actually in general there are no formal methods for converting between an implicit equation for a surface and a signed distance function, and there is a whole branch of scientific publications and things out there, people looking at different ways of solving this problem in the general case. But for us, for now, we're not going to worry about that. So in most cases, the sine distance function has to be derived geometrically for the specific object, and we will look at some interesting examples of that. Okay, so as before, let's look at the sine distance function for our torus. So we're plotting this exactly the same way, x and y both between -3 and 3, and z starting at -2, and as our values of z increase, we see that at z equals 0, we have two circles, two rings in our plot, with exactly what we would expect. Those correspond to the outer edge and inner edge of the torus respectively. And if we continue the animation, we see that, of course, as that plot comes back down again, we see how those shapes relate to the torus shape, as you can see there. Okay, so how could we actually use a sine distance function, and what exactly is ray marching? Well, ray marching is simply a numerical technique for finding the zero crossings of the sine distance function, so the point where the value crosses 0, corresponding to the black in the plots that we just saw. And all we do is to step along a given ray and measure the value of the sine distance function at each point. And we keep doing that until we find the point where the value crosses from being positive to negative. Okay, and this is then the point of intersection between the ray and the object. Now, literally using this approach would be pretty slow, and it would be difficult to ensure that the step size that we were using to step along the ray was right for every situation. It's not really that practical. Luckily, we can make it much more efficient by using a technique that is sometimes called sphere marching. Now, all this does is to use the value of the sine distance function at our current location to decide how far we can move during the next step. And we then move that distance along the ray and then repeat the process. And actually, it's really very simple. So let's look at a quick illustration to see what is going on. Here we go. So in this case, we have our equation here for the sine distance function, as we saw before. Now we're going to start at a point of x0 is equal to -3, y0 equals 0, and z0 equals -2. And if we put those values into this function for fx, y, z, we get a distance of 2.528. So let's consider a sphere of radius 2.528 centered on our starting point. That will look something like this. Okay, so there we are. So what we now do is move our starting point from where we began, which is now the center of the sphere. We move the distance along our ray corresponding to the radius of our sphere. So let's do that. And we see this gives us our new position of our starting point here. So our next starting point is at x1 is equal to -0.739, y1 is 0, and z1 is -0.869. fx, y, z is now equal to 0.608. Okay, so now we create a sphere of radius 0.608, as you can see here in green, okay? And as before, we're then going to move our starting point along the ray, a distance corresponding to the radius of that sphere, and then we're going to repeat the process again. Okay, so now we have x2 is equal to -0.195, y2 stays at 0 in every case, z2 is now -0.597, and the value of fx, yz is now 0.703. So you see the value of fx, yz has gone up. Now the reason for that is because at our previous starting point, we were closer to the torus than we are now. And what the sine distance function does is it gives us the shortest distance between where we are and the surface of the object. So as before, now we construct a sphere of radius 0.7, and you see that will expand until it just touches the edge of the torus. And then we move our starting point exactly as before, and we now see that we have values of x2 is now x3 is 0.433, y3 is 0, z3 is -0.283, and the value of fx, yz is now 1/3, or 0.333. And we simply repeat that process. So we create our sphere of that radius, we move along our starting point, and you can see if we just continue through that process, that brings us exactly to the point of intersection between the ray and the torus shape. Okay, so I mean that's the basics of ray marching, and that is the process we are going to implement in our code in a moment. Okay, so one great advantage of using this approach is that we can derive sine distance functions for all sorts of shapes that would have no equivalent implicit equation. So, for example, the following SDF, which looks a bit scary at first, actually describes a cube. So for any given point P, we can compute AX, AY, AZ, and BX, BY, and BZ this way. So AX is simply equal to the absolute value of PX minus 1. So this is a unit cube, right? And AY is the absolute value of PY minus 1, and AZ the absolute absolute value of pz minus 1. Bx is then equal to the maximum, so this is the mathematical description, argmax, simply to take which one is the maximum of ax or 0. So depending on which is the largest, bx will become either equal to ax or 0. And we do the same for by and bz. We then calculate our internal and external distances separately. Okay, so the internal distances are all going to be negative, and that's given by this expression here. Okay, and the way to understand this, the best way is to break it down. We're taking the maximum of ay and az, and then we take the maximum of ax and whatever the result of that was, and then we take the minimum of that and 0. Okay, so this is going to give us negative values up to 0, right? And then the external distance is simply the square root of bx squared plus by squared plus bz squared. Okay, and then we simply sum those together, and that gives us our final signed distance function. Now, it would be, I think, and I'm happy to be corrected if I'm wrong, but I think it would be impossible to create an implicit equation to describe something of this shape, okay, in some equivalent to this. Let's have a look at actually what that looks like. And we have the same plot as we had before. As we move through that, we see that when z equals 0, we see that we have a square shape illustrated in black, and we have our blue values for negative distances in the center and red values for positive distances outside. And exactly as before, if we continue that animation, then when it comes back down, there we go, we see we do indeed get a perfect shiny cube. Okay, so there we go. That is everything I wanted to talk about for the theory. That's a very light overview of signed distance functions and ray marching. And I've also explained or tried to explain why we might want to use ray marching and why it can be so powerful in terms of what, what it allows us to do. So the next thing that I want to talk about is how we could actually implement this in code. So let's jump in and let's have a look at the C++ code for that. Okay, so before we talk too much about the C++ code, I just want to show what I've done. So I'm in my code folder or directory. If you've been following along, let's just actually run it clean, just tidy that up. Okay, so if you've been following along, you should have something like this. If you've cloned or the GitHub repository or downloaded the code from GitHub, you will also have this code as it is. So we have C app and main. If we go into the QB raytrace subdirectory, what I've done is created a new folder here called QB Raymarch. Okay, so this is, let's just go into that. In the Raymarch subfolder, we now have functions. We have our SDF func, Raymarch base, and then we have classes for cube, sphere, and torus. So we're going to talk about those in a moment. Okay, so the first thing actually to consider is because we've created a new directory, we need to think about our makefile. Okay, so the first thing I've done is to modify a makefile to include a term here for the QB Raymarch folder. So I've talked about this before in previous episodes of how we're using make to manage our build. Okay, and we can simply set this up so it monitors the QB Raymarch directory or folder that we've just created for any changes. Okay, that's it. The only thing that we need to do there is I've created a pair of files, a header file and a code file that contain all of the functions for the signed distance functions. And this, I must confess, isn't how I did it to begin with, but I found this to be a nice way of working. So let's just have a look at that. So this is sdfunc.hpp. Okay, we have our include guards as always, and we hash include qbvector.h from the QB linear algebra library. And then we're defining our namespace. We're obviously using the qbrt namespace, and I've created a new namespace called rm for ray marching, and then a specific namespace within that for SDFs. Now, I don't normally like going to 3 levels of nested namespaces, but in this context, I found it quite useful because I want to call these functions sphere, torus, and box, and I don't want to risk those conflicting with the similar names of classes from the conventional side of the ray tracer. So all we have in there is 3 functions which return, or they all return a double, and they all accept as input a QB vector or a const reference to a QB vector object of type double called P for the point that we want to evaluate, the center, another vector, QB vector object here that describes the center of the shape, and then a QB vector here that lists any parameters that the particular shape will want. You'll notice that the form of all of these is exactly the same. Okay, so we're allowed up to 3 parameters with this configuration. That may turn out to be a limitation later on, but for now it's perfectly acceptable. Okay, So let's look at the CPP file for this. So this is the CPP file for that, and this actually contains the code where we actually compute the sign distance functions that we've just seen in the slides earlier. So for a sphere, it's really simple. We simply do p minus center, okay, and then we simply take the norm of that. We just want the length of that vector, and we minus the radius, which is then given by the first element of the palms variable there, okay. Easy. Torus, it's just an implementation of the sign distance function equation we saw before. We extract x, y, and z from P, and we subtract the center from those, and then we simply have that T1 is equal to the square root of x squared plus y squared minus the major radius, which is given by the first element of palms, and then T2 is the square root of T1 squared plus z squared minus the minor radius given by the second element of palms. Pretty straightforward, and then we just return T2. And the box is simply an implementation of exactly what we just saw. We define a location for our box as being P minus center, and then we compute AX, AY, and AZ as we saw, and we compute BX, BY, and BZ, and then we simply calculate the internal and external distances and return the sum of those. That's really very straightforward. It is a very literal translation from the maths that we saw in the slides to the code. And that's really all we need to do. That is the basic implementation of the sign distance functions for a sphere, for a torus, and for a box. Now, let's have a look how we can actually make that into some kind of practical implementation. So the first thing I've done is to create a base class called RayMarchBase, and the purpose of this is to handle as much of the complexity, it's not really much of the sort of core functionality of implementing these ray marching shapes. So again, this is in the QBRT namespace and in the RM sub namespace, and we have our class RayMarchBase that inherits from ObjectBase, ObjectBase being the original base class we have for all of our objects. We have obviously a default constructor and a destructor, sorry, and we override the test intersection method from the ObjectBase, and we have some new functions here, set object function, okay, because I'm going to use function pointers to do this. And what I wanted to do is I wanted to create the base class to be as generic as possible. The base class handles calculating the points of intersection, okay, and the way I've done it, the reason I've done it this way is it just makes everything as transparent as possible. So as far as the rest of the ray tracer that we've already written is concerned, these objects behave exactly the same as anything else, okay. So, and each implementation, as we'll see in a moment, say for a sphere or for a torus, creates a function pointer that points to the relevant function to evaluate the SDF for that shape, okay, and then it passes that function pointer back to the base class. So anyway, so we have this function set object function that allows that to happen, okay, and then we have a function to evaluate the sign distance function at a given point with the given parameters. Okay, the other thing that we have also is a bounding box. Now, I haven't talked about bounding boxes before. In the previous episode, episode 12, we looked at implementing boxes, and I did mention as part of that that one of the powerful things, once you can do boxes, you can make a bounding box. And the reason for that is if the ray that we're considering does not intersect at all with the bounding box, then there's no point calculating anything else for this particular shape, okay, and the point is a box is relatively easy to evaluate, whereas evaluating something more complex like a sign distance function would soak up CPU cycles and take up time that we don't need to worry about. So we create a bounding box is simply an implementation of the box class that we talked about in the previous episode, and we define a variable mparms to store the necessary parameters. Now we have some private things. We have our pointer to the object function, so this is just using std function to define a function pointer. Okay, that's really standard syntax. I have talked about that before, particularly in my pair of videos I wrote on gradient descent algorithms, or implementing gradient descent optimization in C++. So if that's of interest, you want to know more about function pointers, go back and have a look at that video, I think. And we have some booleans, a flag to say whether we have an object function or not, epsilon we're using to decide if we're close enough to 0, and a maximum steps threshold so we know when to stop. We define m_h, I'm going to come back to that in a moment, and we also define these vectors for x displacement, y displacement, and z displacement, simply so those are pre-allocated. They each describe a step of m_h in each of those directions. Okay, so that's the header file, object RayMarchBase.hpp. Let's look at the equivalent C++ code, the .cpp file. Okay, so here we are, RayMarchBase.cpp. Obviously we include RayMarchBase, and I brought in this qbutils.hpp for the moment, but we don't really need to worry about that. That's really just a set of functions I use for debugging. so let's not worry about that. In our constructor, we define our tolerance. We set to 1 times 10 to the minus 3. That's fairly high, but I've actually found it to be good enough. We define the maximum number of steps allowed, which is simply 100. Okay, we don't have any code in the destructor. Now, the interesting bit is the test intersection function. Okay, so the first thing we do is we identify whether an object function has been defined. If no object function has been defined, then there's no point doing anything, right? So we test for that first. And we then check if the object is visible using the m_isVisible flag, because if it isn't, we simply return false, right? No point doing anything else. And then this basic part of the code is now exactly the same for all of our shapes. We copy the ray, okay, which is given by BCK ray, that's given by cast ray that was passed into this function, and we transform it using the reverse transform that's stored in m_transform matrix. Okay, so we talked about that before in the episode on geometric transforms. And we then test for intersections between that transformed ray and the bounding box. Okay, we're using m_boundingbox.testIntersection. Okay, and if there's no intersection with that, then we simply don't do anything and we return false. If, on the other hand, we do have an intersection, we first extract the ray direction into a variable called v hat, which we then normalize. Okay, we start from our current location is the starting point of our transformed ray, and we set our step count to 0, and we evaluate the distance at our current point using evaluate SDF. I'm going to come to that in a moment. Now, our main loop, this is the bit that actually does the work. It's really very, very simple. We simply loop through this while distance is greater than our m epsilon threshold and step count is less than the maximum number of steps. And we simply set the current location is equal to the current location plus v hat times dist. So that's simply moving along the ray and then updating current location accordingly. Okay. Yes, and we then evaluate the distance. So distance is equal to evaluate SDF at the current location with the current parameters. If the distance is greater than 1 times 10 to the minus 6, then we set step count to m_max steps and we stop. And now, I found it necessary to do that. That's probably not the tidiest way of solving that problem, but sometimes, particularly when there was no intersections, I found it could get confused. We use break to drop out of the loop. Okay. Otherwise, we increment step count and we simply go through that loop. Okay, so either that loop will terminate either when step count is equal to max steps or the distance is less than m_epsilon. Okay, so we come back down to here, we check if step count was equal to max steps. If it was, we return false because we have no valid intersection. Otherwise, we have a valid intersection at current lock. So the first thing we have to do is transform the intersection point back into world coordinates, which we do here, okay, to give int point, and we compute the local normal. Now, I didn't talk about this before, but actually, and this is why we use the value of h and we use the x displacement, y displacement and z displacement variables that we saw, because what we're doing is simply evaluating the numerical gradient of the sign distance function at this location. Now, a very convenient property of sign distance functions is that the gradient at any point is going to be a vector that is perpendicular to the sign distance function at that point. Super convenient. So I've done a very, very simple implementation here to calculate the numerical gradient. And so the surface normal in the x direction, just set element 0. We just evaluate the SDF at x2, which is given here, and subtract from that the value of the SDF at x1. Now, normally for a numerical gradient, you would divide that by 2h, I think. But we don't need to worry about that because we're going to normalize the surface normal vector, which we do here afterwards. So that then takes care of that for us. And we then calculate the local normal by using the apply norm function there, which we talked about in the episode on fixing the normals, episode 11, I think it was, if you want to go back and look at that. And then we return the base color and we return true because we had an intersection, and there we go. That's it. Okay, so the last two functions then to talk about, the function to set the object function. So this accepts as input a function pointer, okay, and it simply copies that into m_object function, and it sets the flag m_have object function to true. And finally, we have our function to evaluate the sign distance function right down here at the bottom, which accepts as input the location and the parameters, and it simply returns m_object function location palms, just like that. Okay, that's the really powerful thing about using function pointers. This doesn't have to do anything special. So our class that inherits from this is going to define the object function, create a function pointer to it, pass that function pointer back to the base class using the setObject function function here, and that's it. Everything then works. Okay, so that may seem complicated. Let's have a look at how we actually implement this for a real shape. Let's look at what we would do for a sphere. Okay, so here we go. Sphere.hpp, not to be confused with the sphere, other sphere class in the main ray tracer. This is in our RM namespace here. Okay, so class sphere, this is the HPP file. We just have our constructor, virtual destructor, and a private object function. Okay, of the same format that we've seen before. Notice that class sphere inherits from RayMarch base. Okay, RayMarch base inherits from object base. It means these objects can be handled by the general ray tracing code as if they were the same as any other objects. Okay, let's look at the CPP file for this. I think the really powerful thing about the way I've created this code is that it makes it super simple. The CPP file is literally that, 51 lines of code, including all the comments at the top. So in the constructor, the first thing we do is we use lambdas to create a function pointer for our object function, okay, called f, just like that. And we return, if you want to know more about this, there's more explanations of doing this sort of thing on Stack Overflow and other websites, so I don't want to go into that too much right now. And all that does is return, this little function here then simply returns the pointer to the object function belonging to this specific instance. Okay, that's important, right? Okay, and once we've defined the lambda, we then use the setObject function from the base class to set the object function to f. We modify the bounding box to make sure that it will fit. Okay, for different things you might want to play around with that to work with the parameters to estimate what size the bounding box should be, but I just set it to 1.2, 1.2, 1.2. It only needs to be centered at the origin because we're using our local coordinate system and so on. The destructor has no code, and the private object function is super simple. Okay, it accepts as input a pointer to a QB vector object with the location and a QB vector object with the parameters. We define our center because we're defining a sphere fixed at the origin in its local coordinate system. So our center is simply 0, 0, 0, and we can fix the parameters because we want this to be a unit sphere. So as I've talked about before, we use geometric transforms later on to modify everything. So all our shapes are defined as unit shapes in their local coordinate system. Okay, so we simply set the first parameter to 1, the other two don't matter. And then we simply return the value of QBRT : RM : SDF : sphere. So that is the sphere function that we saw earlier, and we simply pass to that the pointer to the location and our center object and our int palms object there, and that returns the value of the sign distance function at the point location. Okay, that's it. It's really that simple. And just to show that, let's look at a different shape. Okay, so for a torus, this is torus.hpp. The HPP file is exactly the same as for the sphere, except it has a new function here called set radii, because we have two radii for a torus, R1 and R2, the major and minor radius. Okay, but apart from that, everything is the same. We have initial values of those defined down here. There is one additional function that we have here called update bounds, which we can use to update the size of the bounding box if R1 or R2 have been modified. So let's look at the CPP file for that. Okay, so there it is. Now, as for the sphere.cpp file, this is really very simple. The format of the constructor is exactly the same. We use the lambdas to define our function point f. We use setObject function to pass that back to the base class, and then we set our transform matrix for the bounding box accordingly. We have no code in the destructor. The function to set the radii, that's new, accepts as input R1 and R2, and simply sets the first and second element of m palms accordingly and calls update bounds. Now m-palms, it's important to know it comes from the base class. Okay, so we haven't had to worry about defining that here. We have our function to update the bounding box, which is a little bit different because it just makes sure that the bounding box will fit around the torus. There are some issues with that if you rotate the torus. If you really want to use this code for something, you might want to play around with that. And then most importantly, the private object function, to which we create the function pointer, is exactly the same format, and all it does is define the center point to 0, 0, 0, and then it simply calls QBRT : RM : SDF : torus, the torus function from our set of SDF functions, passes the location, the center point, and palm. So it passes palms from here. Notice we're using star palms because we want to pass what is pointed to by that pointer, not the pointer itself. Okay, same with the location. And that's it. That then implements a torus. And the box shape is exactly the same. I'm sure you don't need me to run over that. So let's go to the terminal, let's compile, and let's just show that this does indeed work. Okay, so I'm back at my terminal window, just going to run make, let that run through and compile everything. So that's compiled. So let's just run /QBRay and let's have a look what we get. So that will run through, and you'll notice because of the use of bounding boxes, it runs very quickly where there are no objects, and it slows down when it comes to the new ray-marched shapes, and then it will speed up again when it goes past them. That's really the power of using a bounding box around things. It can make a massive difference to the performance of a ray tracer. And there we go. So there we go. There is our basic test scene that we've used for everything. And here we have a ray-marched sphere, a ray-marched glass donut, just kind of showing off a bit there, and a ray-marched cube, which clearly demonstrates that the code we've created does indeed work. And ray marching, as I said, allows us to do some really quite exciting things. We can do a lot more beyond these simple geometric primitives, but really just as a quick demonstration, I thought that was adequate. And like I said, this is meant to be a tutorial on ray tracing, not ray marching, so I didn't really want to talk about it too much. Anyway, there we go. That's really everything that I wanted to talk about today. We've looked at ray marching, the theory of ray marching, and a basic overview of how it works, and we've looked at also why we might want to use a technique like ray marching as opposed to conventional ray tracing. And we've also then gone on to have a look at how we can implement ray marching in C++ code as part of the QB Ray Tracer project that we've been developing over the last 12 episodes. So I really hope that's been of interest. It's been a great deal of pleasure making this video. I really hope you've enjoyed it. If you have, please do remember to hit that like button. It really does help with the YouTube algorithm. And if you haven't done so already, please consider subscribing to my channel so you don't have to miss any future videos. I do try to post regularly. Sometimes various other things do get in the way and there's a bit of a gap, but generally I try to be as regular as I can. If you subscribe, you don't need to worry about missing anything. Thank you very much. Anyway, I think that's enough for today. So as I said, I really hope you've enjoyed the video, and yeah, but I really look forward to seeing you in the next one. Thank you very much for watching. Bye.